Hello and welcome back to our Intro to Cassandra for Developers Crash Course. This is video 5 of 7, the art of data modeling. So in the previous sections, we got into some of the basics of data modeling, things like what's a table, what's a key space, what's a primary key, so on and so forth. And that's great for building up that base set of knowledge, but then what happens when you actually want to start data modeling in Cassandra? What does that look like? So that's what we're going to do in this section. So the first thing we just want to do is kind of review some terms so we're all on the same page, right? The first one we see here is normalization. So if you've done any work with a relational database before, normalization is probably going to feel somewhat familiar. This really came from a time where disk space was not cheap and disks were not fast. So normalization is really the process of reducing the amount of redundancy, setting up data integrity and such like that. And so you go through this process of normalization with your data, and then you come up with something like kind of what you see here on the right-hand side. So we've got a very simple example where I've got two tables. I have the employees table and the departments table. And in the employees table, I'm going to find out, okay, who are my employees and what information do I have with them? But let's say that they work in various departments. Now in a normalization method, most likely, I'm going to separate the departments out into a separate table. And why do I do this, right? Well, this comes down to the data redundancy piece. I don't want to have a bunch of redundant data. I want to have a single instance for everything that exists, every type or whatever. So I'm only going to have one engineering department, one math department. And then I'll use these relationships. I use what's called a foreign key to then make a relationship between one table and another. So if you notice up in the employees table, not only do I have a user ID per user, but I also have a department ID. So I'm making that connection back to the departments table. But again, I only have one instance of each type, if you will. So another thing to kind of point out here is that for normalization, there's some pros and cons, right? The rights are pretty darn simple, right? If I want to add a new department, I just add it right to the department table. Done, right? No big deal. Data integrity is also a definite pro of the normalization methods and the way we do things with relational databases. The cons, though, really, from a scalability standpoint, imagine now if you're 20 tables deep, right? Where you have all of these joins between all these tables at runtime, right? So you have to read and do all these Cartesian joins and everything. The queries can become very complex as well, again, as you have all of these different joins and you have to bring all these different pieces of data together. So another technique, though, is called denormalization. This is essentially the opposite of normalization, right? So denormalization is a strategy that is used to increase read performance. Now, this is something that in the relational world is generally not used unless you're talking like data warehousing or if you have a particular need for read performance where you need to flatten out the data. In this case, this is something where if you notice, look at the table now. I have a single employees table. And I have the same Edgar Cod, engineering, so on and so forth. But notice that the department column is actually part of the table and I'm repeating data, right? So one of the strategies here is to, we're not worrying about redundant data, right? We're actually saying, yes, data, I can have redundant data. And why? Because in databases like Cassandra and more in the NoSQL world, technology was different. So Cassandra is making a trade-off. It's saying, I'm going to optimize for read performance at scale, and I'm going to use up more disk space to do so. And the good thing is that today, compared to other commodities, other things like memory, CPU, so on and so forth, disk is actually the cheapest. And with solid state drives, things have gotten significantly faster from the time that when relational databases were first created. So we make this trade-off, and this trade-off actually works in this case. So yes, we're going to go ahead and repeat data here. The key difference is this. Notice there's no joins. You don't have joins in Cassandra. I make one read from one row if I want to get, say, Edgar Cod, and I read from that partition. I have all of my data in one shot, right? Again, it is an optimization for read performance at scale. Now, again, some of the pros that I just mentioned, the quick read performance, also your queries are much, much simpler. Without having, say, 20 nested joins or something like that, your queries are very simple compared to a lot of the relational counterpart queries. Now, there are some cons, though. Now, if you imagine, I have multiple writes potentially, right? Depending on where, say, that department data needs to go, I may need to write to multiple tables, where in the normalized relational sense, I wouldn't. I would just write to a single department table, and anybody who had a relationship to that would then get that update. In the case of a denormalized data model, I now may have potential writes to multiple places. And then from the integrity standpoint, you don't have the same type of integrity constraints that you do in a relational database here. So you do have to keep up on that on your own. Again, though, the big reason for this, though, is read performance. And Cassandra is completely built to be able to maintain its performance at scale. That's a key thing. And if you couldn't tell already, yes, denormalization is the data model pattern that we use in Cassandra. So let's look at this from the flow of how I apply my normalization techniques, my data modeling, and then where developers come into play. So in relational data modeling, I'm going to start off with my data. I'm going to analyze that raw data. I'm going to identify all of their relationships, their properties, any entities. I'm going to use that to generate my data model using my normalization data model patterns, my normalization patterns. Then, after that point, from the application standpoint, from the developer standpoint, then we would do what? We would take a look at whatever, the ER diagram or whatever was, designed, whether that's through your DBA, your data architect or whatever, and you would use that as like the source of truth. And you would then determine, well, what queries do I need for my application? And then use that to determine, well, okay, how do I build those up? What tables do I need to join? That kind of thing. In Cassandra, we're going to flip this on its head. Watch what happens. So in this case, we're going to start with our application workflows. We're going to start there with the application. We're going to use that to generate our data model and our queries and everything, and then apply our data. Now, the question some of you might be thinking is, does that mean I need to come up with my queries ahead of time? Yes, actually. And I'm going to go through a process right now. We're going to go through that. So before you think I'm crazy, we're going to go through that process and show you how this works. Okay. Take a look at this diagram. This is the flow, right? So I mentioned a moment ago, we're going to start with our application workflow and our entities and relationships. This a conceptual data model and our application workflow. Matter of fact, for most of us who have been doing relational work or any kind of application development, you're going to recognize a conceptual data model in a heartbeat. The application workflows, this is really just the workflow that your users go through, right, as they are working through your app. I mean, you could literally start drawing out a UI and a napkin, and you've already started to determine like some of the application workflow. Now we're going to take these two things, and then we're going to use that to start generating our conceptual, mapping our conceptual to our logical data model. We'll then kind of refine our logical data model a little bit, then go through any optimizations if we need to, and finally end with our physical data model. This will be the data model we actually implement in the database. So let's take a look. So here is our conceptual diagram. So notice in this particular case, I have users and videos. So imagine that this is for an application that's like YouTube, right? Where I have videos, and when I go to those videos, I have comments on those videos, and users can also have comments as well. So we see this relationship. If you look at users and videos, you can see I have this relation between users commenting on videos and videos being commented on by users. Not only that, notice that both users and videos have a set of attributes, right? Users have an email, they have an ID, videos have a title, a description, so on and so forth. So by using my entity relationship diagram, I can then start to map out what those relationships are going to look like. Now let's move into the application workflow. So again, I have these two pieces, users and videos. Again, it's like a YouTube-like application. So in one case, use case one there, a user opens a video page, right? So they're going to go to some video page, and I probably want to see all the comments for that video. So if you look at the workflow one here, it says find comments related to target video using its identifier, most recent first. So all I'm saying is I want to go ahead and get the comments for a target video, right? So some video I click on, I want to see its comments using its identifier, meaning probably some key, and then most recent first. What am I saying there? I'm essentially just saying I want the comments in time order, because in an application like that for comments, if I have comments in a random order, they're probably not going to make much sense, right? So I want to go ahead and see those at most recent first. Now, if we take a look at the second use case, a user opens a profile. Pretty much in any retail e-commerce app, whatever, the vast majority of us have built and use applications that require us to log in. We have some profile that goes with us. Same deal here. So here, the user logs in, opens their profile. And now we want to see all of their comments, right, across their videos and stuff. So in this case, you see workflow 2. I want to find comments related to the target user using its identifier. Again, probably some user ID or something. again, get most recent first, right? Again, I want to see those in time order. So right now, those two simple application workflows, we're starting to map out what our data model is going to look like. So the next thing I want to do is now generate some pseudo queries based off of that. So query 1 here, find comments posted for a user with a known ID, right? So by some ID, I want the comments. Now, if you look in the right-hand side, you're going to see this little kind of pseudo table, comments by user. So in Cassandra, the convention we use for a table name is whatever the payload is by whatever I'm partitioning by. So I want comments partitioned by user. That's what we're saying, comments partitioned by user. In query 2 there, again, I want to find comments for a video with a known ID. Same deal, comments by video. I want comments partitioned by video. And both of them, if you notice, say show most recent first, going back to that kind of thing where I want them in time order. That's what that means. Now I can take this and I can start generating my queries. Check this out. So I'm essentially saying, get all the columns. So select star, get all the columns from comments by user, where the user ID is some ID. That's it. That's uber simple. That query alone, once you start to see the tables we're going to use, that will get me all of the comments per a particular user. Now, if you look at the second one there, again, I want to select all the columns. That's what that star is, from my comments by video. So I want all the comments by video, where video ID is, again, some ID. This is going to be the ID of the video. That will give me all of the comments for a video. So you notice we haven't even applied any data yet. We literally just started with our application workflows in our entity relationship diagram, and we're just starting to map this out, and we can already generate some of the queries that we're going to use. Okay, so let's take a look at what this looks like when you start bringing in to the logical data model. So if you notice here, I have our two tables again. Now let's start on the left with comments by user and see that we have user ID. So user ID, that K means it's a partition key. So if you remember from the previous section, we talked about some of the components of the primary key are the partition key and or clustering columns. K means partition key. The C there you see with the arrow means clustering column. The arrow means the order. So what we're saying here is with user ID, I want to, again, this is the comments by user table. So I'm partitioning by user. So I am partitioning by user ID, and then I'm ordering on creation date and comment ID there. You see that? Notice the arrow for creation date is down. I'm saying it's descending, right? What's that going to do for me? Well, that means it's going to show them in descending order. So I'm going to see the most recent first, right? So if I just select star from this table with no other constraint, I'm immediately going to get the very latest comments in descending order. And then the rest of the information is just my payload, so video ID and comment. If you take a look on the right-hand side, comments by video is essentially the same thing. The only difference is I'm now partitioning by the video ID, and in my payload, I have the user ID and comment instead of the video ID and comment. Now you might notice here, I'm repeating some data. Yes, right? It's denormalized. And again, like we said before, in Cassandra, we use a denormalized data model. That's why, we do that again for read, optimized read performance. So what this means is in each one of these cases, I can then do a single read to get all the data back for the question that I have. Okay, so now this is starting to map out our logical data model. Let's move over to the physical data model. So I want you to see something that just happened here. I'm going to go back. Notice creation date and comment ID. I want you to watch what happens. Oh, I lost a column. What happened? Well, now as I start to map out my types and everything as part of the physical data model, so you see that user ID has a UUID. I'll talk about that in a moment. What I want you to notice is comment ID then got collapsed down to a time UUID. What happened there? Well, I used to have two columns, creation date and comment ID. And as part of going into my physical data model, there's an optimization that we performed. I just encapsulated those down into a single type, a single field, comment ID. A time UUID is a combination of a timestamp and a UUID that you can put in a single field. It's a nice optimized type of field for Cassandra. Now, to be sure, if I implement my data model like this, would there be any problem? No, right? I'm going to use a little bit more space and such, but it's not that big of a deal. So it's just an optimization. You don't have to do it, but I just want to give you a feel for the types of things you might optimize when you're moving from your logical data model into your physical data model. So now I've got my user ID as a UUID, my comment ID is a timestamp and a UUID. So combining both created at and common ID into one field. My video ID is also UEI ID, and then comment here being text. Now, the next step is to map this to tables. I mean, it goes that quick, actually. Once you get used to this pattern, it's actually pretty straightforward. So notice here, if you're familiar with SQL, this should look familiar. This is CQL. CQL is a subset of SQL. It looks very familiar to it. But you'll notice my create table, I have create table, if none exists. My table name, comments by user. I have a set of my fields, their types. And then notice my primary key. If you remember, we designated a partition key with K. So my primary key, that first field with the parens again, I have user ID, comma, and then my common ID is going to be my clustering column. And notice that with clustering order, that clustering order by common ID descending, we're saying I want it descending order. That way later on, when I read this data out, I do not need to do an order by. I do not need to pay the cost of an order at read. It is actually being saved in order on disk. So when I go to retrieve it later, not only do I get everything in one partition by that one user ID, but it's already in time ordered format. So this is all optimized for your read performance at scale, right? And again, this is whether it's 3 nodes or thousands of nodes to ensure that you can maintain your tight SLAs at any scale with Cassandra. Okay, so that's the overall process. That's it. You can start with your application workflows. You work those out. You use those to generate your pseudo queries, your pseudo tables. You start to then just refine. And notice, because in a denormalized data model, we don't have all the joins and everything, the queries are actually extremely simple. And so you can take that to just generate your queries. Matter of fact, the general idea is query per table, right? One query per one table, and you'll be off to a good start. Okay, so thanks so much. Let's go ahead and get into an exercise and kind of reinforce some of what you learned.